Okay, well, good morning to everybody. Let me introduce myself. And okay, this is going to be introduction to topological phases of matter. Okay, so what is so let me start with some words, okay, about it. And if you want, you can, this has been a subject of the Nobel Prize of 2016. So if you want to have a elementary introduction, you can see the press release of the Nobel Foundation. You go to the Nobel site and you see there are two documents. One is for the press, which is really elementary, and another one is more technical. So you can start from the first one. In fact, I'm basically repeating the simple one now, and to have an idea is not bad as a starting point. Okay, and so what is a topological state of matter? So it's usually it's in insulating system. So there is a gap in the bulk. So there are no, and you put yourself at low temperature or at energy below such a gap. So usually you would say, what happens in a system when I put energy below the gap? Nothing. In a normal system, there is just a ground state, okay? And in these topological states, topological phase, in fact, mostly is the property of the ground state. So sometimes you say topological states of matter because the ground state is really relevant. Well, the ground state is alive. So it has some features that show up at very, very low energy below the gap. And these features are a particular way to react to the boundary condition. So if you change boundary condition, the ground state changes. And there are global degrees of freedom, not local degrees of freedom. So there are no local fluctuations, but kind of global degrees of freedom. Sometimes, in most of the case, the system has a boundary, so you have massive excitations at the boundary. Okay, and so it is very peculiar. And I mean, the first time you find it is a bit strange, but then after a while you start to think about it as a possible thing. And so most important is a class. Now we understood in the last maybe 10 years or less than 10 years that in fact there is a large class of systems. The first example is quantum Hall effect. And this has been known since the 80s. But and it was meant to be very peculiar, so very high magnetic field and very low temperature. Like let's say 10 millikelvin. Okay. So it was meant to be peculiar state of matter. But now we understand that there are many other cases without a magnetic field in 2-3 dimension, 1 dimension. So there is a entire class of states. So usually the phases of matter are characterized by symmetry, spontaneous symmetry breaking, and the fact that there is an order parameter. Okay. That's a standard picture that you have. If some of you knows the Landau-Ginzburg theory, so there is a theory, there is an order parameter, which could be magnetization or some other, that takes a expectation value, and you have a temperature, and you have a kind of a symmetric phase, and a broken phase, okay? And so that's a critical temperature, maybe. Okay, that's the typical situation. In the topological states, there is no such order parameter. The effective theory is not at all Landau-Ginzburg, but in fact is a gauge effective theory. So there are gauge degrees of freedom. Instead of a scalar field like this, you have a gauge field, a mu, which can be the external electromagnetic field, or can be some kind of internal gauge field. The fact that you have a gauge symmetry it complicates the matter and gives you phases, topological phases, Aron bomb phases, Dirac phases. So very strange phenomena which are related to the fact that the basic degrees of freedom are gauge fields. Okay, so my specialty is to apply field theory to these systems, but in these lectures I will not speak about quantum field theory, but basic quantum mechanics, so that everybody can understand, I hope. Okay, and so this there is no order parameter. Instead, the ground state and the property of the ground state are characterized by exact numbers. So, there is a different topological states characterized by some integer number. So you have an index which takes, you have some quantity which is made, which could be made of this gauge field a mu, or could be made of some other smooth property of the state of the system, like the density or some other property, and this function of the some smooth quantity of the system is an exact integer. So it's so-called topological invariant. Okay. What is a topological invariant? A topological invariant is a quantity which is independent of smooth deformations. So if you vary a little bit some parameter in the Hamiltonian, if you vary, if you define some observable and you, for example, a loop variable, and you deform a little bit the loop, or if you imagine that the system does not lie on a flat surface, but maybe on a curved, this is not curved, okay, in a curved space, and then this deformation do not change this quantity, which is in fact integer. So an integer cannot be deformed. Okay. So topological invariance, topological symmetry means that a quantity is invariant under smooth deformations. Of course, this is understood because you have a gap, and so all these remain, all this quantity remain invariant as long as you don't close the gap. Okay, so this is a generic idea of adiabatic change. That if you take a quantum system, has a gap, and you do perturb a system with a injecting very small energy below the gap, the quantum state remain itself. That's the basic idea of adiabaticity. Okay. So the first example is the quantum Hall effect, which is electron in a two-dimensional layer. So typically, we will talk this next lecture in more detail. So you have a kind of a semiconductor wafer, okay, in which you constrain the electron to stay on a plane, and you put a magnetic field. Okay, that's the quantum Hall effect. Then there are other systems which are generically electrons in a lattice. So you have a band electrons. So you have a conductor bands and you have a valence band. So there is a gap because the system is insulator, so this is filled and this is empty, okay? So this is an insulator. And then what happens in the under certain circumstances, this band system has some massless states. So in the quantum Hall effect, the massless states are at the boundary. They go around like this, okay? And here too, there are some, in some occasions when it becomes topological band system, then you may have one state which crosses, okay? And or two states that cross like this. So that would be a fermion which is chiral, okay? Chiral fermion. So that, for example, in one dimension, the energy is proportional to k, and there is no corresponding mode with minus vk. So this other part is not present, okay? So this is a possibility, and you already see that this system is somehow, this picture already shows you that it is kind of invariant under smooth deformations, because if you have such a state connecting the valence band and the conductant band, then you can deform it a bit, okay? You can deform the band, but it remains there, okay? So the appearance of this, instead, if you have two, maybe you can deform them. For example, if you have two, okay, you may think you can deform it and like this, okay? But with one, it's more difficult, or sometimes impossible, okay? And so these systems, which are band insulator but have topological properties, they occur in many fashion. They have fancy names which are called Chern insulator. Let me write it. Chern insulator. Chern insulator. Then you have topological insulator, topological superconductor. Then you have yeah, more or less this. In fact, it turns out that there is a classification in 10 classes. 10 classes in any D. So for D equal to 1, 2, 3 space dimension, which is in fact in one-to-one correspondence with the classification of random matrices. So there is, I'm afraid I won't be able to tell you much about this, but just to say, this, so there is a classification, and then one of the open problems is to, in this set of states, to find some rational understanding of what are the specific properties. So it's not the the order parameter or the properties. So the basic idea is in all these things is to find universality classes. Okay. So you group the system according to similar properties. So universality classes in normal system with the order parameter, we know what do they depend on. Depend on the dimension of the space-time, the dimension of the order parameter, and the symmetry of the system. So you may say I have a spin model with a spin 1/2 or spin 1. I have ON symmetry, this type of things. They identify the different universality classes. This work for topological states is not completed, is more involved. There is a first classification in 10 classes according to the property of symmetries, elementary discrete symmetry, which are P, T, and C. So parity, time reversal, and charge conjugation. But this is not the end of the story. So it's going on, this analysis. And so the main point is, by analogy, to characterize the the features of these integer numbers, of these topological numbers. These topological numbers appears also in quantum field theory in the property of anomalies. Maybe if you've done some quantum field theory course, you know that there are anomalies and that the integration of anomalies gives topological quantities. So there is a relation with anomalies, but I will not talk about it. Okay, and there is a relation with topological properties in quantum mechanics, which is the Berry phase. Is anybody of you acquainted, has been acquainted to the Berry phase? Raise your hand. Oh, it's fantastic. Fantastic. So, okay, great. So this simplifies a lot my work. Well, fantastic. I'm amazed. So we don't do this in Italy. Okay, great. Okay, so I will be very fast then. Okay, so it's a beautiful idea, you know. I learned recently, so I'm much behind you, you know. So maybe I not understood completely. Maybe you can teach me because I just learned it. Well, it has to do with some magnetic field in a disguised form, okay? So, well, the first thing to understand is there are topological excitations. So I will start discussing topological excitations. So topological excitations is an excitation of the system, of a normal system like a superfluid or superconductor, which is associated to a topological number, to one of these topological index, okay? So this is so the difference is that with topological state, it is the ground state which is associated to a topological number, not the excitations, okay? So in a normal state, for example, in a superfluid, you can have a vortex, and the vortex is associated to a topological number. So this is not a topological state of matter, it's just a property of the excitation. In the topological state, a topological phase of matter, the phase is associated, the ground state is associated to an integer. So let me start by reminding what is a topological index of a vortex. Okay. For example, you have the order parameter, which has a phase. Okay, has a phase, and sometimes the phase has goes around the point. Okay. So, for example, if you have a vortex, and so you draw this phase, so this is a, wow, sorry. So this phase is like a unit vector, so it goes around like this. Okay. And what is the topological number? The topological number is 1 over 2 pi d mu of theta, okay? And so this you integrate, it is 1 over 2 pi theta of, let's say I have an angle here, phi, theta of phi, so phi equal to pi, minus theta of 0. Okay, so this is a vortex in a superfluid. Okay, so this is an integer. Okay, because it depends how many times you wind around it. So if I plot this function, so this is a radial coordinate phi, and this is the angle of the phase of the order parameter. Then you have so a vortex is characterized by the fact that after you wind around this loop, gamma, okay? Then you end up here, okay? So that's the situation in which you get 1, okay? So as you wind around the loop, then the angle or the phase of the order parameter makes a 2 pi, okay? Okay, and so that's then you know that this situation is invariant under smooth deformations, because this is a smooth deformation which of the angle that you wiggle a little bit this thing while you go around, but the endpoint is the same, okay? Then you will have another class which is where you get 2 pi, 4 pi here, okay? That's E equal to I equal to 1, this is I equal to 2, okay? So then you can define so-called homotopy groups, okay? You say this map theta is from phi to some other circle, which could be U1 space of this phase, okay? This is a U1 phase, okay? And then this map can be characterized, associated to equivalence classes. So there are the class which up to smooth deformation goes back to 0, the class that goes back to 2 pi, the class that goes to 4 pi, okay? And then you say, okay, that the map is equivalent to another map if they have this same endpoints, okay? And this is an entity, so this homotopy classes theta, okay? They form a group which is the fundamental group pi 1, okay? Pi 1 of the target space, which is U1, okay? So what does it mean? It means this is a starting point. You define a function on a circle S1. That's the starting point. So you consider quantity defined on a loop. So the loop is a topological equivalent to a circle, okay? And this is a starting point, and this is the target. So which is another S1, another circle, okay? So this is the group of how many the elements are the windings, multiple windings of the circle into itself, okay? So this is a fundamental group. Okay, so you have a topological group, and then you have an index. Index is the value, this quantity, which takes integer value in the different classes. So you have a trivial class with I equal to 0, first class with I equal to 1, I equal to 2, and -1, -2. Okay? So exercise. Draw an example of a vortex with I equal to -1. Okay? It's an exercise in drawing, not physics, but you know, helps. Okay? So that's the idea of a topological quantity. Okay? The simplest one. So there is a U1 degrees of freedom, so a phase, and is defined on a one-dimensional space, which is the loop. Do you have questions so far? Did you get it? Please. Yes, yes, yes. So this is a vortex. This is like a charge of excitation, no? So I is the charge of the excitation. So I equal to 0 is just the ground state. So, and I equal to 1 is vortex 1. I equal to 2 is 2 vortices. Okay, and it's like charge. Okay, and you see that this configuration is orthogonal to the ground state, because you cannot deform, you cannot decay this into the ground state, because by smooth deformation you cannot bring this down here. Okay, you cannot bring the, you cannot once you tangle the phase of the order parameter in this way, you cannot disentangle. Okay, you can by smooth deformations. In fact, by continuity, the order parameter should go to 0 here, because otherwise it's too singular. So in fact, at this point, also the density at the point goes to 0. Okay, because otherwise this point would be too singular. Okay. So this is like a charge of like a charge of a particle. Okay. Okay, now to discuss the topological phase, we need something else, which is another number, which is related to this number, the winding number, but is called first Chern class. It's a fancy name, but you know, mathematician likes a fancy name, and so we have to adopt this. So, first Chern class is another index. It is the two-dimensional on a two-sphere. So it's a flux of a magnetic field through a two-sphere. Okay. So we will need this, and now we discuss a bit of mathematics related to this. Okay. First Chern class. Okay, is it possible to have a magnetic field, a flux of magnetic field through a closed surface different from 0? No. Well, no, and then yes. So that's the trick, okay? So no, but in fact yes. So that's the story. That's the story of the Dirac monopole. Okay, so how do you make a Dirac monopole? Well, you take a solenoid. Okay, everybody knows a solenoid. Okay, so what are the flux lines? Well, the flux line like this. And of course, if you take, for example, this point and you draw a circle, then the total flux is 0 around this point. Okay. But how you make a monopole? A monopole is very simple. You stretch this solenoid so it becomes very long and very thin. Then you send one extrema to infinity, and you end up with a monopole. Okay, that's the idea. So you send this thing to infinity, so it goes to infinity, and you concentrate on this point. Okay, at this point the line goes away like this, and I say, oh, well, that looks like a charge, like an electric charge. So there is a flux around the electric charge, which is 1. Oh, okay. So there is a flux here. But for this string, where all the flux is going away, okay, here is entering. Sorry, this is getting out. So the smooth part is getting out, but there is a very singular contribution which cancel in this point. Okay, Okay? But in fact, we will show that it's possible to dispose of this string, and then you end up with a non-zero value of the flux. Okay? So let me show you this. So we are going to erase the string. Okay? It's possible. Let's see. Okay. Going too fast, or it's okay? It's okay? Okay. So how is this configuration? Well, this configuration of B is going to be G over 4 pi. This is just the charge, the usual electric field of a charge, okay? But I put a coupling constant, which is G, the magnetic charge. And then there is the contribution of the string, which is okay. So I put the axis. Okay. So this is delta function. This is step function. Okay. Okay. So if I now integrate okay, in this way, then I get this is just a constant. I take a sphere, so this is just a constant on the sphere, so I get a solid angle, and so from this part I get G. Okay. And from this part I get another delta function, okay, but then because of orientation is opposite here, then I get minus G. Okay, that's it. Okay, so this is a configuration. This contribution from here, and yes. So it's opposite direction, so you get a minus sign. Yes. Okay. Now we solve for the gauge potential. Okay. So we are going to write this as wedge of A. Okay. So let me take now. So let me take a polar coordinates, theta, okay, and r. Well, okay. So this point will be on a sphere, and I consider now a certain loop gamma, which is the fixed theta angle. Okay. Okay. So then I consider the integral of ds dot okay, so this also okay. I use this formula, okay, and then I integrate. I find out what is A from this, okay. So so let me take this loop here, which is fixed theta. So in fact, this is, and I suppose also that A does not depend on theta. So this is going to be 2 pi A phi, okay. the component along the loop here. Okay. Okay, that's it. Yes. Now I say, okay, which part I take? So I take the upper part, which is smooth, and so I avoid the string. Okay. I take the upper part, and because this is just constant on the surface on this top part of the sphere, then it's going to be just g over 4 pi. So this is sigma, the solid angle. Okay. This is solid angle. Okay. Solid angle, which is okay. So I integrate this thing from 0 to a certain value theta. Okay. To this cap. Okay. And so the result is 2 pi over g over 2 4 pi okay. Then I have to reconstruct the Cartesian coordinates of A. Yes? 0 and theta. Okay? To integrate this cap, I go from here to here. Okay? It's okay? Well, now how to get this is in polar coordinate, is a vector in polar coordinates, so I have to get the vector in Cartesian coordinate. So I remember that ds square is plus r square, the square. Okay. So I get that the norm of, suppose that A has only one component, the norm of A, okay, is also AI square, okay, or if you want A square. So then okay, so then I have to obtain the component in the Cartesian coordinate. I have to divide. I have to take the square root of the inverse metric component, which is this. Okay, so that gives me a sine theta to the denominator. Okay, so in the end, A is just 1 over r sin theta g over 4 pi 1 minus cos theta direction of phi. Okay, and phi is just a unit vector, which is minus sin phi, sorry, phi minus sin theta x plus cos phi y. Okay, So that's the solution for the gauge field. Okay? So you see that this solution has a problem because it's singular for theta equal to to 0. Okay, no, for theta equal to 0 is not singular, but for theta equal to pi it is singular. That's the point where the Dirac string is. Okay? Pi, yes, pi. So for 0 it is not singular. For theta equal to pi it is singular. What's the point? Okay, when you close, okay, you are integrating over this upper cap, okay, and that's the problem. So, but in fact, the point where I put the string is somehow my choice, okay. So I might consider another situation in which I put the string in another direction. Okay, for example, I put the string upward. Okay. So let me call this A plus because it's obtained by integrating the upper cap. Okay. Then I take another gauge field which is obtained in the same way by integrating the lower cap, and I put the string upward. Okay. So you do the same, only you integrate about in theta, not from 0 to zero to theta, but from pi, from theta to pi. Okay, so integrate it from theta to pi. Okay, so what is this other field? Okay, so this is obtained by integration, and the minus sign is obtained because of orientation of the loop with respect to the surface. Okay, so then in fact then I discovered that so this is going to be not singular for theta equal to pi, but singular for theta equal to 0. Okay, so this is string at theta equal to pi, and this is string at theta equal to 0. Okay. So then what? Then what? Well, you say, okay, let's see what is the difference. So which one is right? Well, they are both right, because in fact the relation between the gauge field and the gauge potential is up to a gauge transformation. So they differ from for a gauge transformation. Okay. So if they differ from by a gauge transformation, they are both right. Okay. And so the idea is that I'm going to use both. Okay, I'm going to have if the string is down, I use the one in top. If the string is up, I put the one down. Okay. So I resolved this problem of the singularity by describing this magnetic flux not with a single gauge potential, but with a pair of gauge potentials. Okay. So let's check that the difference is indeed a gauge transformation. Okay. So I use again the polar component. So I say A phi component plus minus A phi component minus is G over 4 pi 1 minus cos theta plus 1 plus cos theta. Okay. So that is G over 4 pi. So that has to be d phi of some gauge field, some gauge transformation. So that's true. If I take chi of phi, G over, 2 pi, G over 2 pi phi, that's a gauge transformation. So they differ by a gauge transformation, okay? But there is a thing. So where is this gauge transformation? Well, this gauge transformation, you can say, okay, I have this sphere, I cover it with two patches. It's a manifold, so a manifold of this kind is covered by two patches, okay? And it makes sense to define the gauge field in this way, provided that this gauge transformation makes sense on the superposition of the two patches, okay? In the area where the two patches overlap. So along the equator, okay? So along the equator you have this gauge transformation U, which is e to the I electric charge chi, okay? Which is e to the e G over 2 pi, okay? So to make sense of it, it has to be periodic, okay? So this element is this gauge transformation is an element of U1. So it should be a periodic function along the equator. So this has to be phi, okay? So then you have, it has to be periodic. So that's to be E I N. So let me say it better. So U of 2 pi of phi equal to pi equal to U of 0. Okay? So that tells you that this has to be e to the I n phi. So that implies that Eg equal to n, 2 pi n. Okay? Okay, so this construction works if this is the proper gauge transformation. Proper gauge transformation means that it is well defined on the overlap between the two solutions. Okay? Yes, please. No. No, you forget about the string. The string does not exist. And now I give you another argument by which it will be more clear. Okay? So where is the string? Does disappeared. Okay? Wait, okay? So this is a Dirac condition, okay? So Dirac arrived to a point to say that, okay, a magnetic monopole could be okay if the magnetic charge and the electric charge are related by this thing. In fact, if I put there is an H bar here, okay? So it's a multiple of H bar of H, okay? So this is the point of view of differential geometry. So that's a modern point of view. You have a manifold, which is the sphere, and then you have a U1 bundle that is at any point you define a element of the U1 group, okay, and A is the connection, so it tells you how to take derivative going from one point to another in the group space. Okay, it's a covariant derivative. With A, you make a covariant derivative. Okay, and so this U1, this A is a U1 connection, and one connection is well defined when the gauge transformation on overlaps are well defined. Okay, so that's a modern point of view. But let's go back to the Dirac point of view. And Dirac point of view was the following: it's equivalent because of the H bar comes from it will be clear in the other thing. Okay, it is in definition of the physical quantity. The physical quantity is yes, you. Say it again. Here. Yeah. I was about to say yes. No, I'm not joking. Come on. Okay, so what was this is professor tricks, but I'm joking. So what was the original argument? Was simpler than that. So he said. So let me go back to the monopole, okay? Okay. So then he said, Dirac asked himself, do I really see this string? Well, let me take a test particle which goes around the string. Okay, I have a test particle, and this goes around the string like this. Okay, let me say far from this smooth part. This smooth part goes away like 1 over r square, and then very far you still have this string. So do I see this? Well, no, because in fact it's true that in quantum mechanics the gauge field, the gauge interaction comes to the gauge potential, not the classical field. So, but it comes to the exponential. So what really matters in quantum mechanics is so-called Dirac phase. Dirac phase is exponential of a mu, or if you want the interaction e to the I a scalar v dt. Okay. If you take a test particle, you put the gauge field, then you get this term into the Lagrangian. But the Lagrangian does not make sense. It's exponential of the Lagrangian. So what happens in the path integral? Okay, where it happens? It happens in the wave function or in the path integral. If you take a system with a certain wave function, then you switch on a gauge field, then it will acquire that phase. And here, in fact, you have the H bar and also the C. Okay? So all the effect of the gauge field is through this phase. Okay? So let me compute this phase for a test particle going around the string. Okay? So I go back to the magnetic field, so that will be the integral on the surface of B. Okay, but B has a delta function singularity here, so I get G. Okay, so the phase is G, yes, am I right? Is the flux through this point, or let me write also the flux. The flux of around the loop, and so this is G. Okay? So if this is just e to the 2 pi n, then the string is invisible. Okay? So that's the original argument of Dirac. You know, it's this kind of argument that show you how clever was Dirac, okay? Because it's really fundamental observation that in fact it's true that quantum mechanics enter the gauge potential a mu, but to the exponent, okay? Through this, okay? And so if there is a 2 pi n singularity of this kind is not important, okay? You can so the string does not exist. If this is true, the string does not exist.
So far, this seems like an extremely fine-tuned situation. We need the magnetic flux going through that to be, for some magic reason, to be exactly this multiple.
Yes, yes, that's the point. It is possible if if this quantity is an integer. Okay, so that's the origin why this quantity, the first Chern class, is an integer. Yes? Yes. So, yes. So the Aharonov-Bohm effect is when you violate the Dirac condition. Okay? So if you violate the Dirac condition, then you, for example, if G is a fraction, let's say G is 1 over kappa, where kappa is an integer, then you get a fraction. Okay? This is the let me write it. Aharonov-Bohm phase. Okay? But that's is a different is going to mix up your ideas. So the Dirac condition tells you that it's possible to have in quantum mechanics a smooth configuration with a non-zero magnetic charge. Okay, that's one point. Then you say, okay, that's one point. Then you go one step further. And you say, okay, what if I don't respect this? Well, you will have an effect due to this string, but that's a different story. For example, I may have excitations which have both electric and magnetic charge, and if the magnetic charge is fractional, then they will have phases. If I bring one excitation around the other with such a fractional magnetic charge, then I will get such a phase. This phase here, I bring one around the other. So for example, I imagine I have a system which is of these fractional strings somehow. In fact, if you have a two-dimensional system, a point particle can have a sort of string magnetic charge attached, which would be a sort of string in the hexadimension, but the hexadimension is not there, so no problem. And so when I bring one around the other, I get a fractional phase e to the 2 pi over k. Okay, this is called fractional statistics, and in fact it takes place in the fractional Hall effect. It is possible to have these fractional magnetic charges in 2 dimensions. But that was not the point I was making. I was trying to argue that it is possible to have a non-trivial magnetic charge which is integer in the proper thing. Okay, so maybe few more minutes or too much? Well, maybe it's too much. Okay, let's stop now. Okay. Okay. So all so all this discussion about the monopole was to introduce you to the fact that this index, which is the first Chern class. So now I put E equal to 1, and also H bar equal to 1, and also C equal to 1. Okay. By the way, show this exercise. Show that this is not possible, but anyhow. Okay. So this this first Chern class, this discussion was to make you understand that this, if it is different from 0, is an integer. Okay. Okay. Now maybe you did some course in differential geometry, and you know there are closed form and exact forms. Okay. So this is a two form. Okay. The magnetic field is, let's take the gauge field in two dimension, and then this F mu nu is just okay, or 1/2. Okay. Sorry, no, 1/2 here. And so this is just integral of one form over two form. So the two form. Sorry. This is a two form, and this is the integral of a two form. So this is the surface integral is antisymmetric. Okay. So in short, this is written as F. Okay. Integral of two form over S2. Okay. So how this can be integer? Well, because in fact we have that F is closed, but F is not exact. To tell the truth, in fact it is exact, but not on the entire space, on subspaces. So in fact F is written as a collection of two 1/4 on the upper cap that I can call sigma plus and sigma minus. Okay. Okay. So how comes that a form can be closed but not exact? Well, it is exact, but only on the subspace of the entire space. So it's not globally defined. Okay. So it is exact. It is exact, but not globally defined. So this is a situation in which you have this A is not globally defined. It's defined on subspaces. Okay. So then you know you can define this as integral on d plus on sigma plus so because in these the two subspaces this is well defined, then you can use the Stokes theorem. Okay. And then you say, okay, this you can use the Stokes theorem, but this is subpart, okay? The subpart and the other subpart are not compact, they have a boundary, so then you get the contribution from the boundary. The contribution from the boundary is okay. This story, okay. And because this is a gauge transformation, okay. So in mathematical terms, you have a U1 bundle. So you have a U1 bundle in which the gauge connection is not globally defined because of some singularity somewhere. Somewhere, not exactly in this, because on the surface, well, there is some singularity somewhere, okay? And then you have to divide it into patches to get a well-defined thing. And then when you do this Stokes theorem, you end up with an integer. So the fact that this first chain class is an integer is again related to pi1 of U1. Okay. So with respect to the vortex, the quantity is two-dimensional, not one-dimensional, but we end up with the same topological class. Okay. So these chain classes are associated to two topological groups. In this case, is the same pi1. Okay. The same, so also called fundamental group. Okay. Okay. So to conclude the story, you can have this quantity is topological. Well, it is topological because you see, in the end, it only depends on the behavior of the gauge field on a subspace on this part. So if I do a small deformation here of the gauge field, so I change a little bit here, because of the Stokes theorem, it won't alter the result. Okay. Also, if I put a metric on this on this space, it does not depend on the metric, because you see this integral of a two form on a two sphere does not involve the metric. Okay, you don't need G mu nu to define this integral. So this quantity is also invariant by deformation of the base space. Suppose that the sphere has some metric, then you deform a bit, it doesn't change. Okay. So all this argument was to make you acquainted to the fact that you can have this topological number. Okay. So this topological number will play a major role. Now I have to tell you next subject, the Berry phase. So the Berry phase will be a way to introduce a gauge field like this in quantum mechanics, even if such field is not apparent. Sometimes it is there. You build from the wave function, and the non-trivial case will be exactly when this quantity is different from 0. Okay, please. You want to do this integral on a genus 2 surface? On a torus? Well, it's the same. It's the same. So you know that this quantity is associated to this group. Okay. So this has to do with loops. So if in your surface you can make a loops, non-trivial loops, then you can get something different from 0. Okay? No, because you have on the torus you have at least two non-trivial loops, one here, one here. So the space of gauge a mu of gauge potential on a torus it includes also these special cases. Okay. For example, I can take two patches, and then I will have to sew them here, and I can have a gauge transformation. Okay. Okay. So now let's discuss a simple quantum mechanical problem in which all of this comes about. Okay. I'm sorry, this lecture and maybe part of the next one will be mathematics, but if you don't, I mean, I think that, well, it's not so bad, no, that as mathematics. Okay. So what is the basic system to discuss the Berry phase? So Berry phase of one spin in a magnetic field. Okay, so what is the Hamiltonian? Okay, is this? Well, there is a minus sign, in fact, but I don't put the minus sign because it's messy. Okay, so these are the sigma matrices. Sigma 1 is 0, 1, 1. Sigma 2 is 0. Sigma 3 is. You can also have a constant here, but let me start without constant because discussing the eigenvalue problem, it doesn't matter. Okay, so I want to study this eigenvalue problem as a function of h. Okay, so what are the eigenvalues? Well, because h square is h square, okay, there are two eigenvalues which are h and minus h, and then you have h equal to h. Okay, it's a spin 1/2, so there are two states. Okay, and now I want to study this system as a function of the parameter h. Okay, because the modulus is not. I mean, the problem is insensitive to the modulus of h, because it's just an overall constant. So I can consider the sphere made by the angular part. Okay, so I say that h1 is h cos, no, sorry, sin theta cos phi, h2 is sin theta sin phi, h3 h cos. So the parameter space of this Hamiltonian, parameter space, not space, parameter space is in fact a two-sphere, as before. Okay, with okay. So now let me study what is the what is the eigenvalue problem as a function of h. Okay, so what is h? H in I substitute is cos theta sin theta. Okay, so then this H is a two-dimensional vector, and you easily find that this is cos theta alpha theta alpha. Okay, so this is a solution. Okay, now I can also put an arbitrary phase. Okay, because state is defined up to an arbitrary phase. Okay, so now look at this this state. Okay, this state is peculiar because it's not globally defined. I mean, very strange, huh? For example, theta equal to 0, you get e to the I alpha 1, 0, and at theta equal to pi, you get e to the I alpha 0. Okay? Okay, so let me take first alpha equal to 0, for example. You see that at the theta equal to pi, this is not single valued because e to the I phi is not well defined at the bottom. Okay, what is the value of phi when you get to the bottom of the sphere? Okay, here. So this as a function of H is not this state, this eigenvalue problem is not globally defined. Okay, say okay, well, let me fix for example phi equal to minus. Another possibility is to say, okay, phi is equal to minus phi. I can change, or yes, and then I will get something which is e to the minus I phi 0 and 0, 1. That's another possibility. Okay. But then this is not well defined at theta equal to 0. Okay? So this state is not, this eigenvalue problem is not globally defined in the parameter space of H. Okay? There is a sort of singularity in this quantum mechanical problem once you see it as a function of the parameter space. Okay? Okay? So you start to smell the analogy with the monopole. Okay? So now let me introduce. So why should I care? Well, you have to care because you can imagine to vary the direction of the magnetic field adiabatically. Okay, so I say, okay, I have the magnetic field up. So here, I mean, everything is fine. Okay, I don't care about going to minus h. Yeah, but then you may imagine an experiment in which you slowly rotate the magnetic field from theta equal to 0 to theta equal to pi. Then you are going to get some trouble. So in principle, there is a trouble because you start from a state and then at the end you end up with a singular state. So there is a problem, okay? So if I want to adiabatically change this one given state and make it complete tour around this sphere, which is also called a block sphere sometime, then you may have a problem. Okay. So then we have this idea of the Berry phase. So what is the Berry phase? So I want to vary h in time slowly. So vary h of t slowly. Okay. Okay. So if I start from a given starting point, let's say h0, and then I do this deformation slowly, I know from the system has a gap because the other state is separated by a gap of 2h. Okay. So the system originally has a gap. So I can do adiabatic transformation. The system. So when you perturb a system in general, the new state will be a superposition of all the states in your spectrum. If you do adiabatically, so if you the rate by which you inject energy is below the gap, okay, then the state will remain itself. So what can be the effect? Then it can acquire a phase. Okay, if you slowly varying a state adiabatically, then the state can acquire a phase, but does not. You don't have transition to another state. Okay. Okay. So what will be this state? This state will be, let me call psi of t. So this is the instantaneous solution of the time-dependent Schrödinger equation. Okay. So this is what you have at any time is a solution of the with respect to t of psi of t should obey the time-dependent Schrödinger equation. Okay. Then you have the states which I introduced before, which are solution of eigenvalue. So for any given value of h, you have a solution. You have a spectrum. You have a eigenstate h. Okay, that I call h. That in fact depend on t, but because I vary h, okay, I vary h, but this is not. This is a solution of a stationary problem. Okay, so I vary h, let's say from here to here, from h0 to some h of t. Okay. Okay. At any time, the state, I know what is the solution. At any given time, I know what is the solution. It is this state solution of the eigenvalue problem at this point. Okay. Let me also, for simplicity, remove the constant and say that h of t is equal to 0. Okay? I remove the constant. Okay? So let's say this is a ground state of this system after introducing the proper constant in the Hamiltonian. So this is the eigenstate of the problem at the given value of h. Okay, but then when I change the magnetic field, it won't be exactly this state because there is this effect of the derivative. Okay, but because of the adiabatic principle, that could be just a phase. A phase multiplied by the h. Okay. Okay. So this is explained. If you want to read more, this is explained in appendix of Sakurai book, and also that I'm using, and also if you want to. You can also solve exactly. So you can solve this transformation h of t even when it is not adiabatic. Okay, so you can solve completely the time-dependent Schrödinger problem, and this is done in another book, Griffiths. another book of quantum mechanics. So if this is, my analysis is taken from this, and this is exact solution. So yes, exact solution. So then you take exact solution. So in general, if it is not adiabatic, the state will be a superposition of the two states. Then you solve, because it's a simple system, and then you check the limit in which the adiabatic approximation works. Okay, which is the rate of change is small. Okay, you can do, but I don't do it. Okay, so then the time dependent state will be a phase times the instantaneous values of eigenvalue problem. Okay. Okay. So now I compute this phase. Okay. Okay. So yes. So okay, H is normalized. Okay. And then I take the following fact: psi dot, because it's normalized, this is orthogonal, it is 0. And this, if I bring through the derivative like this, I get u dagger u dot plus h dot. Okay. So and which is also equal to minus I. So I substitute the time-dependent Schrödinger equation, h of h u h plus, oh sorry, no, this is it, yeah. Okay, and okay, and this is also equal to minus I psi u h of h, which is again 0. Okay, I just check it 0 equal to 0. Okay, but then because this is 0, I get that u dagger u dot is minus h derivative with respect to some parameter lambda I, or if you want derivative with respect to h dot. Okay, and so h is a function of time and also function of theta and phi. Okay, so there will be h of theta of t, phi of t. Okay, because I'm moving on the sphere. Okay, and then u exponent of minus I gamma ai h dot dt, where which is also exponent of minus I of a. Okay, Amy, yes. No, you is just a phase. Yes, I apply the Schrödinger equation. Okay, I commute the u because it's just a phase, and then I check again that it is 0. Okay, I check this, but you would know as well that okay. The wrong point is that I assume only these states, while in general, if it is not adiabatic, I have to sum over all the states. Okay? So I remove this sum. So in general, there will be a matrix, transition matrix. Okay? Yes, please. Where?
You say the left hand side is 0, but it can be, it just has to be imaginary.
Here?
Extremely on the left, because you also have the psi dot psi term in the differentiation.
No. I take derivative of this, is derivative of this times derivative of this. Okay, so you don't believe in this. Okay, but anyhow I prove this 0 on this side. Okay, so this is the Berry phase. So this is the Berry connection, and the Berry connection is AI is in general a vector, because you may have that this derivative involves several components. No, for example, here is just one component, but in general you may have several components. Or if you want seen as a function of theta and phi, you will have an a theta and an a phi. Okay, in this problem, because you can, okay, you can have here, let's say, parameters, okay, lambda I and lambda I dot, okay, and then you have H lambda I H, okay. So this is the Berry connection. Okay. No, wait. Okay, so now you say, but the phase of the state is not well defined, because if I now start from a different state, because I'm allowed to put an arbitrary phase, it depends on the point. Okay? If I do this, then I discover that A transform as A plus d by d lambda I alpha. Okay? So in fact there is a gauge symmetry. Okay? There is a gauge symmetry, so there is a U1 gauge symmetry, because you have this complex space, which is the phase of the wave function. So what it will be, gauge invariant will be only the integral on a closed loop. Okay? So for a closed loop, this phase makes sense, and it is physical on a closed loop. Okay? So the integral on a closed loop is physical. So that means that I take this sphere, I start from some value, then I make a loop and come back. You will say, haha, I go back to the same state. No, because sometimes you get there is this effect of dragging, okay, which was not taken into account in the stationary problem. And this gives you this phase. Okay? And then I say, oh, okay, but this phase is not relevant. Yes, it is relevant when, as I show you before with the monopole, in which this phase realizes a configuration of the monopole. And so it is non-trivial. Okay? And that's because this it occurs when this problem seen as geometry has a bundle. The bundle is non-trivial, so there is a singularity somewhere. So in this specific case, this phase is important, and in fact it has been measured, experimentally measured precisely in this spin 1/2 system. You can measure, you you do this adiabatic process as usual. When you have spin, you compare the rotation of the spin with the magnetic moment, and they have a precession of the magnetic moment, and so you have a comparison, and so this can be observed. And let me show you that indeed this is exactly the same form. Yes? Hmm? No. That you are asking more than what I know. I have read that this is, let me see. The answer that I don't know, but precisely how the experiment is done, but it is described here. And it has been, so this something of the 70s, and it was done at the end of the 70s. So you should compare somehow, not the expectation value, but somehow with respect to a reference state. Okay, so you don't want to compare psi modulo square, but you want to compare psi at t equal to 0 with the return psi after the loop. So this is observable to consider, and so you have to somehow have a way to. It's not a standard observable, but so you should have somehow some other quantity which stay constant during the adiabatic process, and then you compare. Yes, you should have this reference state. Yes. Yes, so it's not a standard thing. But because you can play with different properties of the spin, then I think that's the idea. Yes. Okay, so let me show you that in this gauge field, this is indeed the same thing. Well, because as I told you that if you get a non-trivial Chern class, then there is basically one possibility. So if Chern class is equal to 1, you basically have one gauge field that does the job. And so if you come up with this, it should be the same. In fact, it is the same. And so it's a matter of calculation. Okay? So you do this calculation. So here is the definition. Okay? You plug in. You plug in, so for example, a theta is minus I h d by d theta h, okay? So this is minus I cos theta alpha e to the minus phi sin theta alpha 1/2 minus sin theta alpha e to the I phi cos theta alpha, and you get 0. And analogously you find a phi, which is minus I, well, it is minus I h d by d phi, and you do your computation and you get sine square theta alpha, which is 1/2 y minus cos theta. Okay, and so this is exactly the field of the gauge monopole, what I called A plus before, with G over 4 pi equal 1/2, which is magnetic charge equal to 1. Okay, so this is magnetic charge, so the magnetic charge equal to 1. Okay, then if this was for the state H, then if I take the other state which is singular, so this state H is singular here. Then if you do the computation for the other state H prime with a phase which is singular here, then you will get a minus field. Okay, you get the a minus field. Okay, so indeed this is this Berry phase is the monopole configuration. Okay, and okay, with charge equal to 1. Okay, and so then you can also define the Berry curvature. So it is defined up to a gauge transformation, and the gauge curvature will be f theta phi equal to d theta a phi minus a phi d theta, a theta, which is 0, and this is 1/2 sine theta. Okay, and so the integral of the flux over S2 of this d theta d phi f theta phi is 2 pi times 1/2 times 2 is equal to 2 pi. Okay, so I divided by 2 pi and it is 1. Okay, okay, so this is in fact Chen class equal to 1. Okay, so in this system we have, you can also write f formally like Fij. You can also write formally like I epsilon ij d lambda I h d lambda j h. This is another formula. Okay, so okay, so I have to stop. So why would you like to integrate over H, over the sphere? It's not clear at this point. Okay, so that will be explained later. Okay, that you have to integrate over H. So it makes sense in some not in this physical problem, but in some other physical problem, it makes sense to integrate over H. Please. Yes. No. Sorry. So the phase is through a loop, and so the phase is through a cap. Okay, and that's just 1/2 the solid angle of this cap. Okay, so this is exp I/2 the solid angle swept by gamma. Okay, so that what takes place in the physical problem. Now what I say next, I say, okay, I've got this curvature. If I integrate, I discover that it's the same curvature of the monopole. Or okay, why should I integrate over the entire space? That's another question. In this system, doesn't make sense to integrate over the whole space. But in the system that we will discuss, topological state, it makes sense to integrate over space. Yes? 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 Yes. And the point is that this is singular because of the fact that at h equal to 0 is singular. So there should be a degeneracy in the spectrum to get this effect. No. You do this computation and you get this. It goes to 0. But you know, this is a function of gamma. So if you shrink to 0, you don't do any adiabatic transformation. You just stay on that point. No. The phase, the total phase. So what is physical is the total integral of phase through a cycle. You go back to the original point, and this thing is this portion of the solid angle. But that you choose. Okay, you want to do this adiabatic process, you choose. Okay. So if you do a big adiabatic process, okay, of course, if you by mistake you take the opposite thing, you get the same result up to 2 pi, and so it's the same, okay, because the charge is correctly quantized, okay. Maybe I have a couple of things to say about the property of this berry phase, but maybe next time, okay. Thank you very much.